That is indeed what the title says. So excellent. No, thank you very much for the invitation to speak, and thank you for everyone for coming. Yeah, late in the afternoon. I should start with a preemptive apology. I haven't given a talk with exactly this collection of topics before, so the real thing is that they're all sort of interconnected, and what I want to stress is how they're interconnected. So if I only get through half of what's written on these slides, you'll still have gotten the gist of it, because any half of it allows you to infer the other half. But yeah, so I particularly want to talk about approximate structure, and there's an awful lot of questions you can ask, so I'm choosing one or two of them. Here we go. Yeah, so I think the simplest approximate structure question you can ask, the general format is to take some definition in algebra, and then to ask what happens if, instead of saying that it holds perfectly, to see what happens if it holds most of the time or some of the time, if it holds approximately. So for example, suppose I have two finite abelian groups, and you'll lose not much if you imagine that they're f2 to the n, if that's your favorite finite abelian group. And suppose I have some function from g1 to g2. Then we all know what it means for f to be a homomorphism, right? So f is a homomorphism if for every x, y in g1, f of x plus y is f of x plus f of y. So this is the pure structure. And an approximate structure question, I could ask, for example, I could say that f is a 99% homomorphism if I pick x and y uniformly at random and ask, does this condition f of x plus y equals f of x plus f of y hold? Then that's true almost all the time. It happens with probability close to 1. So if you prefer, an equivalent way of saying it is that the number of pairs x and y for which this condition holds is close to the maximum size of G1 squared. Okay, so that's an object that's sort of almost a homomorphism. It's close to being a homomorphism. And I can also ask, I could say it's a 1% homomorphism if it's a homomorphism sort of 1% of the time, some of the time. So in other words, if I choose x and y at random, then there's some positive probability bounded away from 0 that it obeys the condition for being a homomorphism. And the key question is really sort of, if I give you one of these objects, either a 99% homomorphism or 1% homomorphism, what do they look like? What's the structure of these objects? What can you say if I give you a 99% homomorphism or a 1% homomorphism? Okay, so I guess there's lots of things you can say. If to start off with, I just look at the 99% homomorphism. So this is an object that's sort of a homomorphism almost all the time. So one natural way to come up with such an object would be to start with a genuine homomorphism and then just sort of scramble a few of the values, right? Sort of take a few of the x's and replace them with arbitrary values. Yeah, so if I start with a true homomorphism and I modify, let's say, epsilon over 3 of the values 5x, then I'll definitely get something that's a 99% homomorphism in this sense. The converse isn't obvious. I mean, maybe f has nothing to do with a genuine homomorphism, but as it happens, this is the only way to come up with examples. So everything that's a 99% homomorphism in this sense must come basically from this construction. So this is a sort of folklore proposition, I guess, that says that, yeah, if you're a 99% homomorphism in the sense that I defined, then the only way to get that is to start with a genuine homomorphism and modify constant times epsilon many values. Okay, so somehow the 99% case is, I'd say this is an interesting exercise to prove. It's not trivial. You somehow have to figure out how to fix all the errors in f. Which values should you change? It's not completely obvious. Just to give you some idea of why you might care about this, so the original motivation for this problem was from property testing in computer science. So I'll just describe this in words. So the idea would then be, suppose I gave you a function f, and I promise you that it's a homomorphism. It's a genuine homomorphism. I swear blind that that's the case, but you don't believe me. So you want to test whether this function f is or isn't a homomorphism. Well, obviously, one thing you could do is you could take every single pair of x and y's and see if it obeys the condition, but that might take a very long time if g is large. So a sort of computer science idea is to say, well, what if we just pick x and y at random and check whether it's a homomorphism for that x and y, check if this condition holds, and then repeat that a few times, 100 times or something. Well, one of two things can happen. If this condition ever fails, then obviously what I gave you wasn't a homomorphism. That's clear. And if the condition always does hold, well, what you can deduce is precisely that for almost all pairs x and y, this condition holds, right? If you choose a bunch of random samples and it always works, then then that's what you know. And so it's therefore very interesting to know that that implies that what I gave you was basically actually a homomorphism. That the only way I can lie to you is by lying a tiny little bit. So I must have given you something in the first place that was essentially what I claimed it was. So yeah, so this proposition is really telling you that this algorithm for testing for homomorphisms is a good one. In other words, there are no sort of fake homomorphisms hanging out that sort of pretend to be a homomorphism remarkably well, except the ones that are basically homomorphisms, which is what you want to know. Okay, cool. So that's 99% homomorphisms. So you can also ask, what if I have something that's just a little bit of a homomorphism? So it behaves like a homomorphism a little bit of the time. What can I say about the structure of this object? Well, again, one thing you could do is you could start with a function that's actually a homomorphism, and you could scramble most of the values, right? Just sort of for every x, either take the correct value phi of x or take some other arbitrary value. And I suppose that doesn't always give you one of these objects, but probably it does if you just do things randomly. And maybe that's the only way of doing it, right? So yeah, it seems natural to conjecture, given what we looked at with 99% homomorphisms, that the only way to get a 1% homomorphism is something that's closely related to a true homomorphism. Yeah, so the question is that true for some function of delta, which let's say to start that I just want to know if it's true for any function of delta that only depends on delta. So this question is much harder than the 99% question, in particular because it's not true. So for instance, here's a great example of a function that behaves like a homomorphism about half the time, but is not related to a true homomorphism. So I'm going to take a function from the integers to the integers, and well, you can point out if you like that the integers is not a finite abelian group, and that's fair enough, but it's easy to modify this construction to something that is a finite abelian group. Yeah, and I'm going to take f of x to be take x, multiply it by the square root of 2, and then this notation means take the integer part. So take the floor of root 2x. So if I take x and y to be random integers, and I take the floor of square root 2 x plus y, is that equal to the floor of square root 2x plus the floor of square root 2? That should be a y, sorry. Well, if you think about it, what's happening is that this would be true if you didn't have the integer part signs, and it's going to be true with the integer part signs if and only if the carry bit doesn't move you off by 1. So this equation is either true or it's true off by 1, and each of those happens about half the time. So this will obey the homomorphism condition about half the time. Yeah, so depending on whether the carry bit is a 0 or a 1, it's either true or not. But on the other hand, I mean, the only homomorphisms from the integers to the integers are things of the form phi of x is nx for any integer. And so none of these is going to look anything like this, because this has slope roughly square root 2, and this has slope an integer. So so this is very far from being anything to do with a genuine homomorphism from the integers to the integers. So, okay, so if you work over the integers, the answer is no, as stated. You can modify the question until it has a chance of being true, but that gets somewhat technical, so I won't go into it. On the other hand, if I choose some different finite abelian group, such as my favorite one, f2 to the n, then it's hard to write down examples like this. So it is actually true, it's proved by Samorodnitsky in the early thousands, that if you work over f2 to the n, you have a function from f2 to the n to f2 to the n, then the thing I said is true, that if I have an approximate homomorphism in this sense, it's behaving a little bit like a homomorphism. The only way that can happen is if it agrees with a true homomorphism a positive proportion of the time. Okay. Please interrupt me with questions, by the way, if you have anything you want to know.
If we change that to like any financial field, how will that depend on with the character of the?
Oh, right. Yeah, good question. So yeah, so this is, I've said this for f2 to the n, but it's also true for, for example, fp to the n. For any small p, if you keep p fixed and n large, then this will still be true. And Samorodnitsky got something like f of delta is, I don't know, it's going to be something like delta to some power times e to the 1 over delta, sorry, times 2 to the 1 over delta to some power. And I think all that would change if you move to fp is that you'd replace this 2 by p. Yeah, it's unfortunately this is an exponential bound to start with, and it's an exponential bound that involves p. Neither of those things are good, but probably the dependence on p is the least of your worries here. This is not a very good bound. Yeah, thank you. Any other questions? Sorry. Okay. So yeah, so this is a pretty poor dependence. It's exponential. We don't know of any examples where you actually need it to be exponential. This is just what comes out of the proof. So it's I am going to be somewhat interested in this talk in quantitative bounds. So I mean, it's interesting to know that this is true at all, but you can also ask what's the correct dependence on delta. So here I'm looking at this parameter that says f agrees with a true homomorphism some proportion of the time, but how much of a proportion? How does that vary with delta? And the natural conjecture is that you can take it to be polynomial in delta for some exponent. And okay, if you replace 2 with p, then you allow this exponent to depend on p. So this is a conjecture probably in this form due to Rouge from the 1990s. I'll call it conjecture A. Yeah, this is open for a long time. I wanted to give some brief indication as to why you might possibly care about this. So I think I'll say this quite generally, and then yeah, so I'm trying to give some indication why you might care about this this theorem or this conjecture. So yeah, the superpower it gives you is that you input very, very weak statistical information about f, right? If there's some property that's happening with very small probability, but it doesn't tell you very much. And what you're getting out of it is very rigid algebraic structure. You know that there's a genuine homomorphism phi such that, okay, if you throw away most of the values, f is basically equal to phi. Well, I think this is either an interesting question for its own sake. Maybe you think this is a natural question to ask. This does have some applications, so I'll talk about some later, but there are a number. I mean, there's applications to things like randomness extraction and communication complexity, I guess. But it's also very useful for proving certain things. And the way this tends to happen is, suppose I have some theorem I want to prove about functions f. I want to say for every function little f, something is true. It might happen that for sort of typical f's, for a generic f that I chose at random, I have some argument that shows that, yeah, sort of most of the time for an f that doesn't have anything weird going on, this theorem is true. But maybe that argument breaks down if f has some very particular structure. If there might be some counterexample to some lemma where f is very structured. And it might be the case that, you know, being very structured means having some sort of linear structure, being like a little bit homomorphism-y or something. And maybe I can prove that on the other extreme, if f is completely structured, if f is a homomorphism, well, okay, then I have a different argument, right? I know exactly what f is. I can just check whether the theorem is true for that f. But then there's a gap in between, right? I have the sort of random ones and I have the incredibly structured ones. What happens if it's like a little bit not random, but not perfectly structured? And the idea is that this theorem or this conjecture sort of bridges the gap for you. So you really can split into two cases, handle the things that are pretty random, and then handle the things that are a little bit structured, because the theorem tells you that you can relate them to very structured things. So this is sometimes called the structured randomness dichotomy, that, yeah, you can either you're nothing like a homomorphism or you're a little bit like a homomorphism. And in that case, I can really get my hands on what the function looks like. Yeah, so I'll see a couple of applications later where this sort of thing comes up, but yeah.
The current progress towards this. Yeah.
What's the what? Sorry, the
current progress. What's the known result?
Oh, so this conjecture is known. I'll come to that in a bit. It's known as of very recently. So yeah. So I guess this exponential bound was improved by Sanders in about 2012 to be quasi-polynomial, and then at the end of last year with Tim Gowers, Ben Green, and Terry Tower, we showed that this is true. I can't remember what constant you get here in this formulation, but it's sort of like 20 or something. But yeah, you're stealing my thunder. I'll say this in a second. Okay, any other questions? Cool. So That is now my fault. There we go. So yeah, so this is one form of approximate structure, being an approximate homomorphism. I want to encourage you to think about it as just, you can ask this question about anything you want, any structure you like, take some algebraic property and then say, what does it mean if this happens some of the time, a little bit of the time? Staying with abelian groups for the moment, I know what it means for a subset of an abelian group G to be a subgroup. It's a subgroup if whenever you take two things in the set and you add them together, then they're still in the set. For a finite subset, that's if and only if. And I can also ask, what does it mean for it to be a little bit of a subgroup? So the most natural formulation, given what we've just said, is I'll call this a probabilists subgroup, approximate subgroup, either 99% or 1%. If when you choose x and y from your set at random and you ask if this condition holds, is x plus y again in the set, then this happens with probability close to 1 or just probability bounded away from 0. So that's one formulation of being a little bit of a subgroup. There are many other ways you can do it, though. So what I've called a combinatorialist 99% subgroup, this would say, okay, let's instead take all of the sums, x plus y, where x plus y is in A, and just like see how many things we get when we combine them all together. So this is the set of all sums of two things in A. If A were a subgroup, this set would have size of A. It would be the same set. So I could say that you're almost a subgroup if it only grows by a little bit. If this whole set only accounts for 1 plus epsilon times A elements, and I can say you're a tiny bit like a subgroup if this whole set has size capital K times A, where K is 100 or something, some fixed constant. Okay, and then the natural question is the same one. If I give you one of these objects, what does it look like? What are the interesting examples? And just to fix some notation, so this set, all of the elements x plus y, where x and y are in A, is called the sum set, A plus A. And this number K is typically called the doubling constant. It tells you how much bigger A gets when you take the sum set. Okay, so so just to make sure we're on the same page here, so if I take the following subset of the integers consisting of 1 up to n, well, if I do the combinatorialist approach, then I take A plus A. I can get every number between, that should be 2 and 2n. I apologize. You can get all numbers between 2 and 2n by adding two numbers in A together. And so that has size roughly twice the size of A, give or take. And you can also check if you want that if you choose x and y to be numbers from 1 up to n at random and add them together, then the probability that it still lies in 1 up to n is about a half. So this would be, with either definition, like a sort of 50% approximate subgroup. Okay, and so more generally, if I have either a 99% subgroup or a 1% subgroup, what does it look like? What's true here? So again, the 99% case is pretty straightforward. This was known, I think this goes back to Freiman in the 1970s, probably. This theorem is very strong. It says if you have doubling 1 plus epsilon, where epsilon is any number less than a half, then you're close to being a true subgroup. In fact, you're contained in, well, a coset of some true subgroup, where that subgroup is not much bigger than A. And in fact, not much bigger is just 1 plus epsilon. In fact, slightly more is true than I've written here. Actually, sort of A plus A is just a coset of H. So you don't have to figure out too hard what this H is. It's just all of the numbers you get by adding two things in A. So in this formulation, the only way to get something with doubling close to 1 is to start with a coset and just delete a few points. It turns out you can't add any points because then they keep spreading you out. So so those are the only examples of 99% subgroups in the combinatorial sense. And again, the 1% case is much harder if I have doubling K, for some K is like 100 or something. But it was shown by, I think in this form by Ruja, but it builds on work of Freiman as well, that, okay, you're still contained in some coset, but the coset now might be quite a lot larger than A. We're getting rather a few typos in this. There should be a size of A in here. So you're bigger than A by a factor of K squared 2 times to the K to the 4. So this is a non-trivial theorem. This is called the Freiman-Ruja theorem, and it's not that straightforward to establish. Maybe in this case, it's not too hard. But it at least qualitatively answers this question. And you might notice that this bound I have on the size of H and this bound on Sam-Rudnitsky's theorem are pretty much the same bound. And that's not a coincidence because Sam-Rudnitsky actually proved his theorem by using this theorem. So the two are related. So here I conjectured before that you can just replace this with, this is a pretty terrible exponential bound, but maybe you can just make it polynomial. That would be great. You can't naively just make this polynomial because there's a sort of bad example where you take, if you take A to be n basis vectors in F2 to the n or something, then if you take A plus A, it has size about n/2 times the size of A, but the smallest subgroup that this fits inside is like the whole space, which is exponentially larger than A by a factor that's exponential in n. So naively, you can't just replace the bound here with a better one. But Kaplan Martin came up with a sort of modified conjecture, which says, okay, if instead of putting A inside one subgroup, one coset, I get to put it inside a union of cosets, then I can ask for the number of cosets in that union to be bounded by some polynomial in K. So yeah, this would say that if you have doubling K, then there's some subgroup and a bunch of cosets of that subgroup so that A is contained in all of them. So this is called Martin's conjecture or the polynomial Freiman-Ruger conjecture because it's what you get by taking the Freiman-Ruger theorem and asking for a polynomial bound. I'm going to call it conjecture B compared to conjecture A earlier. And it turns out that these two conjectures are the same. So a common theme with these approximate structure questions is that it's sort of way easier to go from one kind of approximate structure to another kind of approximate structure than it is to prove anything about any one of them. So if you can prove the structure theorem for 1% homomorphisms, then you can also prove the structure theorem for 1% subgroups and vice versa. And in fact, there are many more equivalent statements of this conjecture that you can pass between freely with just polynomial bound losses. So sort of for this reason, the polynomial Freiman-Ruger conjecture has had this sort of central location in additive combinatorics that sort of many other problems branch off it because it has so many equivalent forms. And the way I think about it is that there's really just sort of one notion of having additive structure, and you can think of that as having like homomorphism structure or subgroup structure, and sort of the substance called additive structure can be sort of freely manipulated, at least using modern tools in additive combinatorics. If you don't have modern tools, it's quite hard, but for us these days, it's not too hard. Okay, and just to give a quick idea about how you might do that, suppose I know the structure theorem for approximate subgroups, and I want to deduce the structure theorem for approximate homomorphisms. Here's what I can do. Take this function that's sort of a little bit of a homomorphism and look at its graph. So the graph of that function will be a subset of f2 to the n cross f2 to the n. And it's not at all hard to see that the probability if I take two things in here and add them together that it's still inside this set is exactly the parameter delta from the definition of a 1% homomorphism. So I can go from a 1% homomorphism to a probabilist 1% subgroup. That's not the same as the kind of 1% subgroup I was talking about on the previous slide with this doubling constant, but we have enough tools that you can repair one and turn it into the other. So here you'd need something like the Balog-Semrady-Gowers theorem, but we have a big box of tools that we can use to tidy and move from one formulation to another. Okay. So say the history of this unified conjecture is that Saunders improved this exponential bound to a quasi-polynomial bound, like e to the log delta to the 4 or something, to the 3 later. Then recently, together with Tim Gowers, Ben Green, and Terry Cow, we managed to prove this conjecture at least over f2 to the n and probably fp to the n, but that hasn't come out yet, with a sort of semi-reasonable constant. So it should probably give you some idea as to how that goes. I'm not going to talk too much about the details of this proof because I want to talk about some other things as well. But very roughly, what you do to prove that conjecture is to reformulate it in yet another way. So rather than talking about
Question here.
Oh,
What is semi-reasonable?
oh, I see. So over f2 to the n, semi-reasonable means 12. And for the unpublished work over fp to the n, I think this constant will be something times, I don't know, p cubed or possibly p cubed log p. We haven't quite decided yet. But it's yeah, it's some reasonably growing function of p. It's almost certainly not optimal, but it's not sort of 10 to the 10 to the 10 to the 10 or anything. So that's what I mean by semi-reasonable. Within additive combinatorics, we have a lot of unreasonable constants, which are 10 to the 10 to the 10 to the 10 or something like that. So yeah, thank you. Any other questions? Okay. Yeah, so a very rough outline of how this goes. So if you reformulate that problem yet again, instead of talking about a subset of an abelian group G, I can generalize that to talking about a random variable on G. And the archetypal random variable would just be to say, choose an element of A at random. Yeah, that's a random variable on G. If I have a subset of G, I can talk about its size in order to talk about additive structure. For a random variable on G, well, I could just talk about its size in the sense of its, I could just talk about its size in the sense of, its support or something, like how many different values it can take. But the natural notion of size that you want to use is the Shannon entropy. So if you have a uniform random variable, then its Shannon entropy is just log of its cardinality. But if you have a non-uniform one, it sort of takes into account sort of how big it looks viewed from 30,000 feet. Okay, and then instead of saying that A has small doubling, that A plus A has cardinality at most K times A, the natural analog of that for random variables would be to say, well, take two copies of X independent and look at the random variable X1 plus X2 and look at the Shannon entropy of that and say, okay, this is not too much larger than the Shannon entropy of the original variable. And these are the same random variable, then you don't need this average, but if they're different, then take the average of the entropy of X1 and the entropy of X2. Yeah, and you want this quantity to be at most little k, where little k will be about log of big K. Okay, so that gives you yet another equivalent formulation of the problem, but somehow it behaves a lot more nicely. This measure of Shannon entropy is sort of smoother. You don't have sort of, yeah, it's sort of, there are more analytic tools you can use to analyze it. And the general structure of the proof is rather than trying to find the structure all in one go, you do the sort of iterative thing where you say, okay, start with some random variables X1 and X2 where this quantity is quite small, and then try and find new random variables where this quantity is slightly smaller. So I don't need to find perfect structure in X1 and X2, I just need to make them slightly more structured. If you can do that, then you sort of iterate this again and again and again, and eventually you compress this constant K down towards 0. And once it's very close to 0, you're in the 99% regime and you know what to do. Yeah, this is, I mean, there are many other ingredients to the proof, but that's very roughly how it goes, is that you're looking for a bag of tricks to slightly improve the structure. And as I say, this is sort of easier in the random variable case because there's many more modifications you can do to a random variable than you can do to a set. So it works better.
But these two new random variables, X1 prime, X2 prime, are also defined in the same group G, or should it be a small?
Yeah, no, so they're also defined on G, and moreover, they're sort of related to X1 and X2 in some vague sense that I haven't defined, right? I mean, obviously you can write down just some other random variables which have, this little K being 0 or something, but the point is that they're derived from X1 and X2, so sort of, if you know that X1 prime and X2 prime have something to do with a subgroup, then that implies the same for the original X1 and X2. Yeah, so there's this sort of, some notion of distance on the space of random variables that lets you make this argument work. Yeah, thank you. Okay, I think this is my last slide about this polynomial Feynman Ricci conjecture. So if anyone has more questions about this, then it's good for time. Okay. Yeah, so I'm going to get onto a slightly different topic of approximate polynomials in a few different senses. So like I said, you can apply this approximate structure idea to your favorite area of mathematics. If you're interested in the algebras, I guess you can ask what an approximate subly algebra is or something. I haven't thought about it, but feel free. But one that comes up a lot in applications It's the idea of an approximate polynomial. So suppose I have a function from the integers to the integers. So my first task is going to be to say, well, what does it mean for f to be a polynomial in the sense of some condition that I can check? I mean, I know what it means in the sense of, sort of x squared plus 7x plus 4 or something, but this is sort of a given object. I want to know a condition I can check for being a polynomial. And there's a natural way to do this. So if I had a function on the reals, I would say you're a polynomial if when I take some number of derivatives, I get 0, right? And if I have a function on a discrete group, I can take discrete derivatives. So I just take f of x and subtract f of x plus h and call this a new function derivative of f in direction little h. It's a fact so that if you start with some function and take any kth order derivative of it, and you always get 0, then your function originally must have been a polynomial of degree most k minus 1. And I like this observation because I think I first saw it in middle school, right? You're given this thing where you have a sequence, which is your function f of x, and then you want to know if it's polynomial. So first of all, you take the discrete derivatives of difference 1, and then you take the discrete derivatives of difference 1 again, and then you do it a third time, and then you get 0, and this tells you that your original function must have been quadratic. And then you can sort of go back and figure out what the quadratic polynomial was. Yeah, so this should be an observation that you're familiar with. Yeah, and this exactly tells you polynomials of the shape. I guess for arbitrary abelian groups, I don't actually know what I think of a polynomial from, f2 to the 7 to f3 to the 4 should be or something, but you can use this as the definition. So for my purposes, I'll say that a function between two abelian groups just is a polynomial of degree most s if its s plus first discrete derivatives always match. Okay, and this is progress, right? Because this is some condition that depends on some choice of x and hi, and I can now ask what it means for this to hold sort of somewhat, like some 99% of the time or 1% of the time. So let me do that. So this time there are a few different flavors. This is the one we're used to. I can say you're a probabilistic approximate polynomial if, yeah, whenever I take f plus 1, s plus 2 variables at random and ask if this condition is satisfied for those s plus 2 variables, then probability that happens is delta. And you can put 1 minus epsilon in here if you want, in a 99% case. Yeah, that's a sort of a natural thing to consider, I guess. I suppose if you want the combinatorialist version, like some sets or something, but one thing you could say is, well, if I just take all the different values I get when I take s plus first derivatives and look at the set of those values, maybe I could say that that set is small, has small cardinality. So a different notion, I guess. I want to focus on the third notion, which I'll call an analyst approximate polynomial. And this is different in a few ways. So firstly, instead of taking a function from one abelian group to another, I'm going to take a function from an abelian group to the complex numbers. And let's say it's one bounded, so it's going to the unit ball. So a good example is just assume that it's e to the 2 pi I times some phase f of x, where f is a function from g to the unit circle. And then instead of, so because I've replaced an additive group with the complex numbers under multiplication, I have to replace all of my addition operations with multiplication operations and my subtractions with complex conjugates. So I've just modified this definition by saying capital delta is now this multiplicative derivative. Okay, and then so you'd be a 100% polynomial if this capital delta of h1, capital delta of hs plus 1g was always equal to 1. That would be the analogous statement to be a 100% polynomial. And now I'm going to say, rather than saying that it's equal to 1 lots of the time, I'm just going to say it's sort of biased in favor of 1. So when you take this quantity and you average it over all x1 up to xs plus 1, then this value that I'm averaging is going to take values inside the unit complex disk. And then those values might be sort of scattered around, but they're sort of slightly more often in this direction than in this direction. They sort of exhibit some slight bias towards positive real values. So this is a very, very weak hypothesis compared to the previous ones. I'm not claiming that this number is equal to 1 for any choice of the parameters. I'm just saying it sort of goes a bit in that direction. Okay, and this is what I'm calling an analyst approximate polynomial. One question you could reasonably ask is whether this left-hand side is actually a real number, let alone a positive real number. But the answer is yes. You can show that this is always a real number at least 0. So this inequality is at least legal. Yeah, and in fact, this has a name. So this is the 2 to the s plus first power of what's called the Gauss uniformity norm, order s plus 1. So this is just a name for this quantity, where I take an arbitrary function g. Okay, so I'm really saying you are an analyst approximate polynomial if this Gauss norm thing is somewhat large. Okay. Yeah, so this is our hypothesis that this Gauss norm thing, this iterated discrete derivative is biased towards 1. And again, our natural question is going to be, what do these things look like? I mean, what's the structure of a function g that has this property? I suppose given all the examples that we've seen, maybe we should think that it looks like some sort of true polynomial. But I guess now that would be a true phase polynomial, something of the form e to the 2 pi r psi of x or something. So is it the case that g sort of behaves like e to the 2 pi I times some polynomial? And you also have to be careful what you mean by roughly equal to. And the right thing to ask, I think, is that g should correlate with one of these. So our hypothesis is about like correlating with 1, and our conclusion should be that g correlates with something that looks like a phase polynomial. At least that's a reasonable question to ask. If you have this hypothesis, must you be a little bit biased in the direction of a true polynomial? So a reasonable question. I should say, first of all, that the answer is going to be no, for exactly the same reason as the other cases we've seen, that if you work over the integers, then you can sort of find things that look a little bit like polynomials, but aren't actually polynomials. But maybe it's better to ask this question of a g being f p to the n or some fine. Okay, so maybe I'll say what this does when s equals 1. So this is sort of the first non-trivial case. So now I can expand out this derivative. What I'm asking about is the average of this expression, g of x plus h1, g of x plus h2, g of x plus h1 plus h2, with suitable complex conjugation signs inserted. I'm assuming that this thing is biased in favor of 1. These slides have gone a bit strange. So, and the question would be, does there exist some true linear function, so a character, from g to the unit circle, such that f correlates with e to the negative 2 pi I chi of x? So yeah, given g with this property, does it correlate? Pardon, that should be a g. Does g correlate with some true linear phase? Well, this is precisely the Fourier coefficient of f, right? This is one way to define the Fourier coefficient of f out of chi. So I'm really asking if g or possibly f obeys this condition, must it have some large Fourier coefficient bounded away from 0? And it turns out that the answer is yes, because again, apologies for the s and the g's. This expression turns out to be precisely equal to the sum of the 4th powers of the Fourier coefficients. Using sort of Parsifal's identity and some bounds and some messing around, you can show that, yeah, that there must be a chi such that this is large, otherwise this sum would be small. So this is really Fourier analysis. It's a sort of particular case of Fourier analysis. But it's saying, yeah, given some hypothesis on g, that's the same as talking about g having a large Fourier coefficient. For that reason, the general case where you have quadratics here, or cubics, or higher polynomials, is sometimes called higher order Fourier analysis, because it's really asking about whether this function correlates with some polynomial phase rather than a linear phase. So that's where this higher order comes from, is you replace a linear character with some polynomial phase. Okay. Into my time, so let me see if I can tell you what's true. So yeah, so that theorem that I originally stated, or the question I originally stated, is true, like I said, over finite fields, over FP to the n. So you don't have any bad examples with long intervals or taking integer parts or anything. And yeah, it is true that if this hypothesis holds, then G correlates with a degree of most S polynomial phase on FP to the n. If you care about quantitative bounds, this original proof by Tau and Ziegler, it's building on Bogus and Tau Ziegler, I think, and you want to know what f of p delta is, the answer is there is none. They don't give any explicit bound at all on f of p delta. It comes from sort of compactness arguments and infinitary techniques. But much more recently, Gauss and Elisabich were able to get a quantitative bound here. And the quantitative bound is sort of some finite number of exponentials depending on s applied to delta, which, you know, as I said, many constants in this field are unreasonable. And if you think that getting a bounded number of exponentials is good, then that gives you some impression of what bad looks like. So, but this was a big breakthrough to get any quantitative bounded tool here. Okay, and say, so if you're, instead of working over FP to the n, you're working over, let's say, some cyclic group, Z mod NZ, then this naive conjecture doesn't hold, but we sort of know how to fix it. And the thing you have to put instead of a phase polynomial here is what we call a nil sequence, or at least that's one thing you can put. And it's a theorem of Green, Tau, and Ziegler that this statement is true if you replace phase polynomials with this more general class of objects. So this is fully, yeah, either of these would be the inverse theorem for the Gauss norms. Again, Green, Tau, and Ziegler don't give you any control at all on what f of delta is. But a paper of mine from 2018 shows you that actually you can get away with double exponential in delta. It's sort of bizarre that usually the finite field case is better behaved, but in this case, the cyclic case is better behaved, and I can replace an arbitrary quantity depending on s with 2. As of now, that's the best we know. It's sort of, this problem seems to be significantly harder to get good bounds in than the approximate homomorphism problem or the approximate subgroup problem. Maybe this will change soon. Watch this space, but yeah. So yeah. So this is sort of either of these you can call a structure theorem for approximate polynomials. I think probably the last thing I can say before I run out of time, which is convenient. Oh yeah. So how do you prove these things? So again, all of these problems are interconnected, and the way that you prove the analyst's approximate polynomial question, this problem about Gauss norms, is that you show that it's implied by the normal approximate polynomial problem, what I call the probabilist approximate polynomial problem. So if I rewind a little bit. So I'm talking about this top one where you just say that the derivative vanishes positive proportion of the time. So if you know an inverse theorem or a structure theorem for those things, then that implies an inverse theorem for the analyst version. But the strange thing is that the degree goes up by 1. So if you know exactly what approximately linear functions look like, then that actually gives you the quadratic version of the Gauss norm inverse problem, which is, it happens for a reason, but it's slightly unexpected. So in particular, if what you care about is this U3 norm, like the inverse theory for quadratic Fourier analysis, then what you care about is exactly the structure theory of 1% linear functions. And that's exactly this polynomial Feynman-Rüger conjecture that at least over 2 to the n, we have very good bounds for. So we now have very good bounds for quadratic Fourier analysis and still pretty shambolic bounds for anything higher than that. So that's where we've got to. Okay, and the reason I've sort of harped on quite so much about this analyst's approximate polynomial question, I mean, it's not the first approximate structure question you think of, but it really was motivated by applications. So here's a very brief summary of a proof that you can, famous result due to Green and Tau, that really needs this structure theorem as a big ingredient. So the question is, I want to know how many configurations x plus a, x plus 2a, x plus 3a, in other words, a sort of short-term arithmetic progression where all of the hops have side a. How many of these can you find where all of the 4 points are prime? This is a question they wanted to ask. And yet, if you only take numbers at most n, what's the number of such configurations asymptotically? So in the sort of caricature, I guess, the way that this is proved is that you split into two cases. So in the first case, you say, well, maybe the primes up to n are sort of unstructured. They sort of look like a random set. And for a random set, you know how many of these four-term progressions it has because you basically just flip a coin for each one. So, you know, for any candidate progression, what's the probability that this is in your set? What's the probability that this is in? They're independent. Just toss a coin and then average over n, and that should be the answer. And it turns out that unless the primes have some sort of approximate quadratic structure, you can show by, you know, the Cauchy-Schwarz inequality and lots of other things that would be roughly the right answer. Actually, that's a lie. The primes are structured in some interesting ways. For example, most of them are odd, and you have to factor that in. Otherwise, you get the wrong number. But you can find the correction, and then having found the correction, if they're after that basically look random, then you know what the answer should be. And that is the truth. That is what the answer is. Yeah, the number of solutions is the same as from this randomness heuristic. So on the other hand, maybe the primes do have some sort of interesting quadratic structure. Maybe the indicator function of the primes is a sort of 1% quadratic function in this sort of analyst sense. Maybe that's true. We certainly have to rule that out if we want case one to succeed. But that's asking whether the primes have some very weak structure, whether they sort of have some very fuzzy 1% quadratic bias in favor of something. That's a pretty hard question. But if you know this structure theorem for approximately quadratic things, then that would give you a much stronger condition that says the primes correlate with some very particular algebraic function that I can think of. So there would have to be one of these null sequences, think about it as just a quadratic phase, that the primes correlate with. And that's now a very, very concrete question that you can analyze if you know something about the prime numbers. And as it happens, you know just enough about the prime numbers to rule that out, to say that they can't correlate with one of these null sequence objects. Okay, and so the case two is actually a lie, it doesn't happen, but it's very important that you can rule out case two without knowing everything there is possibly to know about the prime numbers. And this inverse theorem is a sort of crucial step. So this is a sort of example of the general framework of how you apply these statements that I was trying to give you a taste of at the start. Yeah, you know what to do if it looks random, you know what to do if it's incredibly structured, and then somewhere hidden in this line of the proof is to say, well, if it has even a little bit of structure, then I can upgrade that to strong structure. Okay, and I think I'm now out of time. Unfortunately, that's the end of my thoughts, so I'll stop there.
Thank you for really wonderful talk.
Yeah.
Thank you so much for introducing the background and also the frontiers in this area. I believe there must be lots of question and discussion in person or online.
Is there anything known in the non-abelian group case?
Oh, it's a great question. So if you have an approximate subgroup of the non-abelian group, the nicest definition in this case is that you take A times A, and you insist that it's contained in some bounded number of translates of A. It's called an approximate subgroup condition. And it is known that if you obey this condition, you must look like something coming from a nilpotent quotient of your original group or something. So yeah, the only examples of these sort of nilpotent progressions or subgroups or things like that. So this is called screen tau someone. No, I think it's Borgang tau. Yeah, and so this is known, but this is one of these theorems where, as of now, we have no quantitative bounds whatsoever. So the proof of this is truly extraordinary. It says, suppose that the structure theorem fails, take a sequence of counterexamples of size going to infinity, take an ultra limit of those counterexamples, use that to construct a topological group, to which you then apply Hilbert's fifth problem, and deduce that it must be a Lie group or something, and then use that to find to show that they weren't all counterexamples. It's a completely extraordinary proof. We can't quite eliminate proofs like that from this field, but it would be a very interesting problem to get any quantitative bounds at all in this theory. Yeah, but it seems somehow much harder. None of the techniques I was talking about from the PFR thing really apply to non-abelian groups.
I think this is related to some problem for the sum product.
Yeah. So
like an equal group where you both have
It's not the screenshot.
Oh. Yeah, so the sum product question is where you have maybe a set of integers and you look at both a plus a and a times a, where this is normal multiplication, and you ask, yeah, can both of these be simultaneously small? And the answer is no. And I think that has something to do with doubling in sort of affine groups or something. You can certainly reformulate these questions, but yeah, I think some things are known about this, but some things are not known. It's a challenge to get sort of optimal structure theory. Yeah.
Christian.
I have a question. So I look at definitions of the approximate homomorphism. So actually, you are using some property just for semigroup, not for group theory. So I don't think any inverse is considered inside.
Oh, right, yeah. So certainly you can say if you prefer. You could also that condition, which I guess would be a more normal homomorphism condition. But because the group is finite,
Yeah.
Well, actually no, because I'm I think I can just I think this and what I wrote down before are the same up to some change of variables.
Yeah.
So I think it's equivalent. But are you saying you could ask the same question for a semigroup or?
So you define some approximate subgroup.
Oh,
Yeah, that's the
yeah. So that's a bit more subtle. So yeah, in that case, saying that A is a subgroup, if for all x and y in A, x plus y is also in A.
yeah. So
Oh, yeah. So
in
you
this
actually
definition, there's no inverse element. So and
yeah.
I don't think you assume A is symmetric set. So A is no longer symmetric. So
Right. However, yes. So because A is finite,
Yeah.
I'm assuming that A is a finite set.
Yeah.
Then the only things obeying this condition must be these genuine subgroups.
Yeah.
But yeah, you're right. It's not a usual definition of a subgroup. It just
Yeah.
happens to imply it for finite sets.
okay.
Yeah. The one thing you can't do, by the way, is say if you ever want to do the exercise of trying to show the structure theorem for 99% homomorphisms, for example, it's a fun exercise. The one thing you have to remember is that your group has to be associative. Somehow, if your proof doesn't use that fact, then it can't succeed. That's the only hint I can give you about that problem. But yeah. Yeah.
Okay.
Okay, is there any further question? Or is there any online question?
No.
Okay, if there are no further questions, let's thank Freddie again for this nice and beautiful talk. Thank you.
Right.